All right, so this is the beginning of the new chapter on coloring graphs. Okay, so the first topic is vertex coloring. So what is vertex coloring? So we have so I said S be a set of colors. Right, could be numbers, and a vertex coloring of a graph G is a function C from the vertex set to the set S such that adjacent vertices get distinct color. So whenever V, W are adjacent, then you put the different color. So that's the vertex coloring. If S is 1 up to K, then it is called the K coloring. Sometimes it's called the proper K coloring. Here's proper means that adjacent vertices get distinct colors. And we say a graph G is K colorable if it admits a K coloring. Okay, now there may be a different definitions, but for us we're gonna say that only the loopless graphs admit of proper coloring. Is it okay? So if I have a loop, then you can never make CV. Yeah, this is impossible on the current definition, because if I have a loop, V is adjacent to itself. So in our definitions, only loopless graphs are K colorable. I mean, admits a K coloring. But typically, in many cases, people don't care. People just ignore loops and talk about coloring. And the chromatic number is what? Chromatic number chi of G is the minimum K such that graph G admits a K coloring. Alright, so for instance, at K1 you have chromatic number 1, K2 chromatic number is 2 because these two vertices should get different colors. If you have K3, the chromatic number is 3. Right, all three vertices get distinct colors. If you have a C4, C5, then chromatic number is 2. No, 3, because it's not bipartite. So if I put start 1, 2, 1, 2, and then I cannot put 1, so it has to be 3. Another way of looking at the chromatic number is by thinking it as a partition of the vertex set into stable sets. What is stable? A set of vertices is stable if no two vertices in the set are adjacent. Okay, so then what is chromatic number? So chromatic number is at most K, so that's same as saying G admits a K coloring. That's same as saying the vertex set of G can be partitioned into K stable sets. Note that empty set is stable as well. Right? So even if you have a graph which admits coloring with the two colors, you still have a partition into K stable sets, even if K is a lot bigger than 2. All right. Now, let's start with the simplest observations. Okay, so for a simple graph G, chromatin number is at most delta plus 1. All right. Why? Well, we apply induction on number of vertices, and it's trivial if number of vertices is most 1, right? If you have a 1 vertex, then delta is 0. Oh, what? By the way, what is delta? Did I define it? No. Okay, let's define delta. Maybe I might have defined it, right? It's a maximum degree. All right. Now, so we may assume number of vertices is bigger than 1. Let G be a vertex. No, V be a vertex of G. Then by the induction hypothesis, G delivery has a K coloring. What is K? Delta G. Plus 1 coloring, because delta G delivery is less than or equal to delta G. Now, you have a vertex V and degrees and most delta. The number of colors available is bigger than that. There is an unused color. Okay, there is a color unused in the neighborhood of V, so extend the coloring by coloring V with this unused color. Okay, right? Because the degree is small, so you have only small number of colors used in this particular coloring, and since the number of colors available is bigger than that, by Pigeonhole principle or whatever, you must have some color available for V, and you can use that to color this vertex. And it turns out that this is more likely the situation. So many of the proofs about graph coloring depends on the degree, depends on the vertex of small degree. Okay, and this is similar to planar graphs. And you may recall this 4-color theorem. Is chi of planar graph Okay, is every simple planar graph four colorable? This problem has long history. So initially the problem was proposed in 1852 by Guthrie, who was a 20-year-old young man, and he came up with this problem that in terms of his terminology it was a problem on map coloring. So you have a map and you want to color the map, regions of the map, so that adjacent regions, when they share a border, the adjacent regions get distinct colors. Now, if you look at the geometric dual of this map, then you get the planar graph and vertex coloring, right? Because you put one vertex in each regions and then put an edge if they share a border. And then this becomes a plane graph. Right? Am I doing all right? Yes. And then the problem of coloring faces of a map is same as coloring vertices of a geometric dual graph. So therefore, four-color theorem or four-color problem of Guthrie becomes a problem on vertex coloring. And this was, this could have been forgotten, but so Francis Guthrie was not able to find any count example, so he asked to his brother, Frederick Guthrie, and then that brother passed that question to his professor. He was taking lectures at University of College London, and the professor's name is De Morgan. Okay, so everybody may be familiar with De Morgan's law, and he liked the problem. So then what he did is send a letter to his collaborator, longtime correspondent. He sent a letter to Hamilton. You may know this British mathematician Hamilton, who one of the theorem I remember is Cayley-Hamilton theorem on matrices. So he was at the Trinity College at that time in Dublin. And this letter is preserved. So on the internet you can find the actual letter. The actual letter starts with saying that a student of mine asked me today to give him a reason for a fact which he did not know was a fact and do not know yet, something like. So the letter started like this, and he drew the pictures. So this is how we know the origin of the four-color problem. And of course, Hamilton replied to De Morgan a few days later. So this was like, the letter was like 1852, October 23. Yeah. And then Hamilton replied, the mail, saying that he's not interested. So that was it. And then it has been forgotten for a long time. And then 20 years later, Cayley, who was like prominent mathematicians in England, he wrote a paper on it. He wrote a 4-page paper, actually 2-page papers, and submitted to proceedings of Royal Geographical Society and Monthly Record of Geography. So he thought that could be interesting to geographers. Anyway, once Cayley published the paper, and he also asked questions around, even at the conferences, and then many people jumped in to serve it. And then, surprisingly, just 1 year later, in 1879, Kempe wrote a proof and published the proof in American American Journal of Mathematics. So Kempe published the proof that every planar graph is four-colorable. And because of that, probably because of that, he became a member of Royal Society in England. He was actually a lawyer, even though he write papers in mathematics. He graduated from Cambridge in 1872, so he was already a lawyer, but he managed to publish something. And then in 11 years later, in 11 years, so it's 1890, Hewitt found a gap in this proof. So Kempe's proof has a mistake. And then he said that, oh, even though his proof is incorrect, but his proof can prove that every planar graph is five-colorable. So let me show you why every planar graph is five-colorable. Right? It's a similar proof. It's induction on the number of vertices, and it's trivial if graph is small. Let's say if it has at most 5 vertices, you give distinct colors to every vertex, then it's trivial. And now, by Euler's formula, we knew that number of edges of the planar graph is at most 3 times number of vertices minus 6. So sum of the degree of the vertex in a planar graph divided by number of vertices is less than 6. Because sum of degree is twice number of edges. Twice number of edges is 6 times number of vertices minus 12. So it's 6 times, yeah, so it's less than 6. So by Pearson's principle, there is a vertex v of degree at most 6, no, at most 5. Because you have numbers whose average is at most 5. No, average is less than 6, but these numbers are integers, so one of them is at most 5. All right, and if degree of v is at most 4, then we can extend a 5 coloring of G delete v by using an unused color for in the neighbors of v to color v, right? Because if I have a degree 4, then number of colors used in the neighbor is 4 or less. So since I have a 5 colors, so one of the colors remains, so I can extend the coloring by using that color. All right, so that means I can assume the degree of vertex v is 5. Now I will show you 2 proofs. So the proof 1 from here. Now this is the proof that Kempe made, and he discovered that it works only for 5 coloring, not for the 4 coloring. So proof 1 is you came up. So now I can assume that all 5 neighbors have distinct colors, right? Let us fix coloring. Right. So all these 5 colors have distinct colors. So let's say 1, 2, 3, 4, 5 in the cyclic order, and that's the color. And this is V1, V2, V3, V4, V5. All right. Now, let's try to change the color 1 to 3. Let's change this vertex to 3. What will happen? Well, if I'm really lucky, then in this neighbor of this V1, there's no color 3, so it might be okay, but probably that's not the case, right? I might have a neighbor which has color 3. In that case, I have a conflict, right? So let's consider the following. So let Cij be the component of the subgraph of G delete V induced by vertices of color I or J and containing Vi. Okay, so what I mean is I look at the induced subgraph consisting of vertices of color I and J, and in this induced subgraph I choose the component containing Vi. So let's look at C13. So I have one, so this is color 1, and I might have a neighbor which is color 3, and it may have a neighbor color 1, another neighbor color 1, and I might have another color 3 and 3, right? And if that's the component, this is my Cij, meaning that there's no color 1 or 3 in the neighborhood of that. And what I do is, if Cij does not contain Vj, then I'm happy, because so if C13 does not contain V3, so this is V1, V3, then I can swap this color 1 with 3. Swap 3 becomes 1, 1 becomes 3. So swap 1 and 3 in Cij, not 1 and 3, I and J. In Cij, so swap the color I and J in Cij. So then we have a new coloring. A new 5 coloring of G delete V, where the neighbors of V uses at most 4 colors, which is good since it uses only, right, because it doesn't use I. Then G is 5 coloring. G is 5 colorable. Okay, so therefore I can assume, just we can assume that for all this thing Ij, Cij contains both Vi and Vj. Thus, there is a path in G delete V from Vi to Vj consisting of vertices of color I or J, right? So V1 and V3, so you have a path P13. Okay, so this path is called the Pij. All right? And all the vertices of this path have color 1 or 3. And similarly, there is a path P24. Now, here is the contradiction. Where is the contradiction? When you look at this cycle, V2 is inside and V4 is outside, right? This forms a simple closed curve, and any curve from V2 to V4 must intersect this path, right? So P13 and P24 must have an intersection by the Jordan curve theorem. Because V2 is inside, V4 is outside. That's the choice. But this intersection, what is, and because it's planar plane graph, you can only have a intersection at the vertex. So this vertex, what is color? 1 or 3 by P13, and it's 2 or 4 by P24. That's contradiction. Okay, so that's the first proof. Many of you may have seen it in the discrete math course. Second proof doesn't use this. So this argument of using paths is called the Kempe chain argument. So this path is commonly called Kempe chain. So his name remains. Okay. The second proof uses contraction. So let me briefly sketch it. So I have a vertex of degree 5, right? And note that K5 is not planar. So there is I and J such that Vi is not adjacent to Vj, right? So there is a Vi, Vj that's such that these two are not adjacent. Now, if that's the case, then let G prime G contract with Vi, contract with Vj. So we are contracting these two edges. Now, again, G prime is planar. And so by induction, G prime has a 5 coloring. C prime, let's say. Now, let C of W to be C prime of W if V is not equal to V, W is not equal to V, Vi, Vj. And if W is equal to V, then okay, after contraction, let V be the vertex of G prime obtained by contraction. So let's use contraction. Oops. If W is Vi or Vj, we just copy the color of V. Right. So when you have this, 1, 2, 3, 4, 5, you contract it. So this may have other edges, right? So I have a color of this guy. So use that color to color these two, and all others stay same. Okay. Now what you observe is the following. Then C is a 5 coloring of G delete V such that the neighbors of V use at most 4 distinct colors. Because two vertices is the same color. By the way, why is this a coloring? Because whenever you have two adjacent vertices, you have distinct colors. And this is guaranteed because these two vertices are not adjacent. So now we can extend C. The 5 coloring of G. So that's another proof. So I show you 2 proofs. The graph is 5 colorable. Now, this famous theorem, 4-color theorem, states that every simple planar graph is 4-colorable. And this was only proved in 1976 by Appel and Haken. And later in 2000, no, not 2000, 1997, there's another proof, slightly simpler, by Robertson, Simmer, Robertson, Sanders, and Simmer, Thomas. Both proof uses computer. Crucially. And the proof is similar to the proof of 5-color theorem, in a sense that you try to find some configuration in a small area and then you reduce it. Like in the second proof, you contract and reduce. That's the key idea. But to find this reducible configuration, you use Euler's formula and do some inequality techniques. But in the original proof of Appel and Haken, there are 1,936 reducible configurations to study. So the proof says that in any minimum count example to the 4-color theorem, at least one of these, in any planar graph, in any plane triangulation, one of these configurations, reducible configuration, must occur. And if it occurs, then it cannot be the minimum count example. So that's the proof. And the later proof by Robertson, Sanders, Simmer, Thomas reduced the number of reducible configuration to 630 something, 633. So after these proofs, people have no doubt that this is a theorem, but still some of you may wonder whether you can believe a proof written, proof in part helped by computers. Like you may be not sure whether compilers have no bugs or computers have no bugs, etc. Right? If there's any error introduced in the proof, is there any chance that the proof collapses? And then in 2005, Gontier at Microsoft, Gontier at Microsoft, he formalized all the proof into a proof that computers can read. So he generated a proof that can be checked by computer code called the Coq. So there's a system where if you give a proof, then computer system will check whether every line can be deduced all the way from the set theoretic axioms. So he made a formal proof. So that's what's called formal proof. So the computers verify the proof perfectly. So now there's no doubt that the theorem is true. And even with this proof, the proof is like, this computer code is like 19,000 lines. Okay, and then once you give it to the computer, then computer spend like 3 hours to verify the proof. All right. This was in I think it was on the news, like the Nature or Science, long time ago, and he's working on. So before formalizing four-color theorem, Gontier's work also formalized Jordan curve theorem. Anyway, so let me show you the wrong proof of Kempe, and you may check whether it's okay. Since it's wrong proof, I'm gonna use different color, gray. So again, induction on number of vertices, and we can assume every vertex has degree at least 5. Why? Because if I have a vertex of degree 1 or 2 or 3, I can delete it and apply induction and extend the coloring, because number of colors used in the neighbor is small. If I have a vertex of degree 4, then I can use this Kempe chain argument. So P13 and P24, and they must intersect, contradicting the Jordan curve theorem. So every vertex has degree at least 5. By Euler's formula, the average degree is less than 6. There is a vertex V of degree at most 5. So the degree of V is exactly 5. So you have a vertex of degree 5. Okay, so V1, V2, V3, V4, V5. Now you only have 4 colors. By the way, we can assume the graph is a triangulation. I should have written somewhere before. We may assume that every face is a triangle. Why? Because if face is not a triangle, now if face is not a triangle, let's say this. You can maybe add a chord, right? If face is not a triangle, add a chord. Is that simple? Can I always add a chord? No. Actually, there is one case which may be dangerous. If there was, potentially there's a edge like this, then when you add a chord, you are creating parallel edges. So you don't want to create parallel edges. That's a big danger. But in that case, instead of this diagonal, you do that diagonal. Then no longer it will be in conflict with the existing edge because of Jordan curve theorem, right? There's no edge going from here inside of this cycle to the outside. So I can always find some way to add a diagonal to face of length at least 4. So therefore, I can assume that every face is a triangle. So that means I can assume that around this vertex V, it looks like a 5 cycle. Okay. Now, if you have a 5 cycle, what we do is the following. Since all these 5 colors, we can assume, we may also assume that all 4 colors appear in the neighborhood, right? Otherwise, we can extend it. If one color is not used, we can extend it. And let's assume that this color 1 appears here, color 2 appears here, color 3 appears here. 2 vertices have the same color. right? That two vertices could be these two. Okay. All right. So color 4 appears here. Okay, color 4. So let's assume that this is the coloring. And now by our assumption, otherwise we use campaign argument. There's a path from 1 to 3, P13. There's a path from 1 to 4, P14. Okay, so I have 3, 4, 5, color 1, 2, 3, 4, color 2. I'm assuming the color 2 appears twice. There's a path P13, there's a path P14, and how about P24? Do we have a P24? No, because 2 is inside of this cycle, 4 is outside. So that means this component C24 is completely inside. And the component of C53, there's no P53, right? This means, I choose a vertex, I choose a component of consisting of vertices of color 2 and 3 using this vertex. Then it can never escape this cycle. So there's a component here called the C53. And then what we do is change, here it changes 5 with 3, here changes, no, not 5, 2 with 3, this changes 2 with 4. Yeah, so then we get a new coloring where in the neighborhood it looks like this. So they extend the coloring of G delete free to a coloring of G by coloring V with color 2. Okay, so that's the proof in 1879 by Campan. So you may want to find a mistake in this proof. And if you Google this, you can find this paper, initial paper, which is written in English, and you can have a look. All right, so that's about planar graphs. Now let's go back to degree argument. This campaign argument is very useful to study vertex coloring. So here's another problem. So we proved that chromatic number is at most delta plus 1. But is it tight? Is it tight? When do we have equality? And of course we have equality when graph is complete graphs, right? Complete graphs, chromatic number is n, because all two vertices, any pair of vertices are adjacent, and the maximum degree is n minus 1, right? Another example is the odd cycle. If you have odd cycle, chromatic number is 3, but its maximum degree is 2. So that's another example where equality holds. And actually these two are the only examples where this is true. So the Brooks theorem says that that's the only case. So if, as long as the graph is connected, if G is a simple connected graph, then chromatic number is at most maximum degree unless G is complete graph or an odd cycle. Okay, unless graph is complete graph or an odd cycle, the chromatic number is at most delta. How do we prove that? We again use this induction. All the proof looks similar. So induction on number of vertices, and you can use the same idea. So by the same idea, we can assume that every vertex has degree exactly delta of G. Right? Okay, so let's say what's gonna be the, okay, let me move this a little bit. So let me write the claim first. All right, so we can assume that every vertex is degree delta, and now I have a vertex V. And we can also assume that every 5 coloring of G delete V has the property that, no, not 5 coloring. What is that? So okay, let me write this way. If every vertex has degree and most delta, then chromatic number is equal to let me say it this way. G is connected and degree of vertex of G is at most 5 for all vertices V, then chromatic number G is the most delta of 5 delta unless G is K delta plus 1 or G is odd cycle. Okay. Well, you can even do further. Let's not worry too much about odd cycle, because if the maximum degree is 2, it's trivial. If delta is 2, then graphs are either paths or cycles. And then max chromatic number is the most 2 unless it's odd cycle. So it's trivial if maximum degree is the most 2. So let's prove the following. So let delta be at least 3. Then we don't have to have a odd cycle, right? So here's the claim, which we will prove by induction. So delta be a constant at least 3. If graph is connected and every vertex is degree most delta, then chromatic number is at most delta unless chromatic graph is isomorphic to complete graph on delta plus 1 vertices. And this statement we apply induction on number of vertices, and then every vertex is degree exactly delta. We can assume that. Otherwise, we apply induction, and every delta coloring of G delete V. By induction, we know that there is a delta coloring of G delete V, and we have this property that all delta colors appear in the neighborhood of V. Okay. Now, yeah, all delta colors appear in the neighborhood, and that's not only in one particular coloring, but any delta coloring of G delta V has this property. Now here's a V, and V1, V2, V3, V delta. So let V be a vertex. Oh, yeah. Every vertex has the property. Okay, so again the same argument. Let Hij be the subgraph of G induced by the vertices of color I or J. Okay, that's Hij. And same way, Cij be the component. Oh, we may assume. Okay, so let's assume color Vi is I, right? Okay, by swapping colors, swapping labels maybe, and Cij be the component of Hij containing Vi. All right, so now by the Cambrian argument, Cij does not contain Vj, then we swap I and J in Cij, and color v by I, right? So that's a contradiction. Oh, well, that's delta coloring. So we may assume Cij contains Vj. Okay, that we can assume. Now, what else can you assume? What we are gonna do is, now the proof is different from the 5-color theorem of the planar graphs, because we don't have a Jordan curve theorem, so we need to use some other argument. So that already means that Cji is also equal to Cij, because Cji contains Vj, and they are the same component. Okay. Now let's look at this picture. So this is V, and let's say this is Vi. If you have two neighbors of color J, then what can you say? If Vi has two neighbors of color J in Cij, then what can you say? Then here you have a delta minus 1 neighbors other than V, right? Then out of delta minus 1 colors, okay, so this is delta minus 1, so that's delta. Among delta vertices, two vertices have the same color, so that means one of the color is not appearing. So does not appear in V, or it's the neighbors. Oh, neighbors Vi, or neighbors of Vi other than V. Right. So color Vi by that color and color, then I is not appearing in Vi, and color V by I. So that's delta coloring of G. So okay, that's it. So that means we can assume the degree of Vi is 1 in H Cij. All right. So what we are going to prove is that Cij is a path from Vi to Vj. So the first step is to show that this vertex has degree 1 in Cij. Now, second step is to show that all the vertices in the middle have degree 2. Okay, so suppose that Cij has a vertex of degree and more than 2. Okay, now let's say this vertex is W. Choose W so that the distance from W to Vi is minimum. So here's W Okay, here's a W, here's a VI, and this is the first vertex whose degree is at least 3. Now, that means among these delta vertices, all these 3 vertices have the same color, right? Actually, this is delta plus 1 vertices because including this W, you have delta plus 1 vertices. Among delta plus 1 vertices, 3 vertices have the same color. Right? If this is I, if W has color I, then these 3 have color J. So that means at least one color is unused. So color W by that color. So we change the coloring. So the W is now the color different than the previous coloring. Now what happened is that all the vertices here, we knew that all vertices on the path from Vi to W have degree 2 in Cij. So by recoloring, Cij will have no path from Vi to Vj in a new coloring, right? So let me say Cij prime. In the new coloring, we still define Cij as a Cij prime, and there will not be any path from Vi to Vj because everything else is same coloring, so you still have the same component structure, but this was path. There's no way out because every vertex has degree 2, and we are cutting here. So that means Cij prime doesn't contain Vj, so that's contradiction. What I mean is we can swap the color Ij and then extend the coloring, right? So Vi will be colored by J, so we color V by I. So that means all vertices of Cij have degree at most 2 in Cij. So that is Cij is a path from Vi to Vj. Okay, now that's an interesting situation. So we have a V1, V2, V3, and V delta, and we may assume V1 is not adjacent to V2. Why? Because if all the neighbors are pairwise adjacent, then you have a delta plus 1 vertices. I mean, you have a complete graph on delta plus 1 vertices. And then there's no other vertices because everybody has degree exactly delta. And graph will be equal to complete graph. So because G is not K delta plus 1, we can assume that V1 is not adjacent to V2. Oh, I need to prove one more thing. Okay, what happens if I have a Vi and Vj and Vk? Can I have intersections? So claim the Cij intersections Cik is only one vertex Vi. Why? If it does have other vertex, let's say V, no, not V, W. Then let's look at these delta plus 1 vertices. Among these delta plus 1 vertices, 2 vertices have a color, same color. Another 2 vertices have the same color. So when you remove these 2 vertices, then you end up with a delta plus 1 vertices. So the number of colors used in this delta plus 1 vertices is at most delta minus 1. There is a vertex W such that W and its neighbors use at most delta minus 1 distinct colors. Recolor, so we can recolor W by an unused color. That will break the path from Vi to Vj, so that's contradiction. By I mean, I can recolor, I can swap color I and j in Cij and then color V by I. So now we are in the final stage. So there is a V1, V2, and you have a path P12, C12, and you have another path C13. Now let C prime be a coloring of G delivery obtained by swapping 1 and 2 in C12. Okay, we swap the color 1 and 2. So what happened is you have a new coloring where this become 2, 1, 2, and 1. Okay, now define Cij prime accordingly. Right, so everything to the same. And now let's look at the 2, 3. What is the 2, 3 prime? All right, so C23 is actually C. Yeah, so C23, what's gonna happen? It should be a path from this vertex to that vertex, right? I used to have a, yeah, so this is color 3, so 2, 3, 2, 3, right? But the thing is, in the previous coloring, I used to have a path going to here, right? There used to be a path like this. Right, maybe, okay, let's say this vertex is U, right? And oh, 2, 3. Let me think. I want to have an intersection. So where can I have intersection? So 1, 2, 2, 3. So 1. Okay, maybe I will change my proof a little bit. So that was, let's swap 1 and 3. Okay, so this choice was good. But now this is 3, 1. Oops. Alright, so this is color 2 in the new coloring. And now I look at the neighbors of this vertex in this path. So let's call it U. U be the neighbor of V1, which is now V3 prime in C prime 2, 3. No, actually it's 1, 2. Yes. Oh no, it's C12. Yeah, so I used to have this C12, so this is 2, 1, 2, 1, and 1, right? Previous, so this used to exist. One, 2, 1, 2, 1. So this is my vertex U. So that's U. And but because I changed the color 1, 3, this becomes color 1. But I knew that none of the vertices on this path intersected with U, so I know that the color of U doesn't change. I mean, of course, color of U was 2, so nothing changes. Now, in the new coloring, U is in C12 prime because C12 prime is equal to C21 prime, and it's contained over here. And U is in, and also U is in C2, C3 2 prime, which is equal to C2. Yeah, C2 3 prime. Okay. Now that means U is in the intersection of C21 prime and C23 prime. That's contradiction. Because U is not one of these vertices. Right? Remember? By the claim, right? If you have two paths, you never have. The only intersection is at the vertex, which is neighbor of V. Alright, so that's the proof. Yeah, so that's the proof of Brooks theorem. So in the next lecture, we will talk about edge coloring. Okay.